So let's welcome back everyone and good afternoon. This is the final talk of the Professor Stefano Morra on complete cohomology of Shimura curves. Yeah, I think we can start. It's 12 noon now. Yeah.
Thank you. Thank you very much for the introduction. So we are going now to conclude this course, this short course about the completed cohomology of Shimura curves. So the outline for today is the following. I will start with some reminders about the Ecke action on the completed cohomology, then the relation with Galois representation, and my goal is to end up with proving the flatness of the completed cohomology over a certain local Galois deformation ring over R bar restricted to G FP. All right. So Ecke algebra. So what are we going now to do? What is the outline now? Now we would like to define an action of an Ecke algebra on the completed cohomology so that we can relate completed cohomology and Galois representation. So first of all, the Ecke operators. So I just recall you. So this is paragraph 5.1. Ecke algebras. Don't hesitate to tell me if this is readable, or maybe you prefer another pen. Maybe this is better. Okay, so
I think it's okay for me.
Okay, thank you very much. I will try to use this one as long as it works. So we take G, an element in the finite adelse, and I pick a compact open K, compact open subgroup in the adelic point. Then, well, what happens is the following, is that we have the following Galois cover, K intersect with G, Kg minus 1 over C. And we have two ways to go back to Yk over C. Sorry, I said that it's Galois cover. It's not a priori Galois cover. One needs some condition about the subgroup with respect to K. So here we have the inclusion. And here we have the right multiplication. By G. And hence, we can define operator at the level of cohomology as follows, as a pull back and push forward. So here we have our H1 of KW. We have the Ecke operator, which I call TG, to H1 KW, which is just given by, so we pull back the trace map on cohomology, and we push forward the right multiplication. Okay, so now, if I pick a place, where my quaternion algebra is split and the level is maximal compact, I define very specific such operators. So if I pick L is a finite place such that BL is split. So here we have FL. And moreover, we have that we have that K at L is isomorphic to GL2 or FL. Then we define the operator TL as the double coset operator. So meaning that we define this operator as the operator T associated to 1 by L. So this is the uniformizer at L. And we have also SL, which is defined by the operator T at this central element. So what happens now is that if we consider the following abstract algebra, so if I take the tensor product over all L as above, so just remember, this L should always be different from P. Okay, I take L as above, and here I take the polynomial algebra over O in the variable TL SL. So what I want to remark is that this polynomial algebra is actually the double coset algebra, thanks to the Cartan decomposition. So I take here KL, G, QL, here I have again KL. Okay, so this is FL. So this algebra, this is a restricted tensor product, this algebra acts over my cohomology space. And I define the IK algebra to be the faithful quotient acting over here. So I define P, K, W if I need to specify the coefficient. So this is by definition the faithful quotient acting on my cohomology. Sorry, KW. All right, so what happens now if I change the level? So now if I can pass to the limit over compact normal compact open subgroup. So now we can consider, so call this algebra H K upper P. So now we can consider the following. We can consider that if I have some smaller compact open at P, we have natural surjections. So here I have K upper P, K prime and lower P of W naught omega S. So this surjects to Tk upper P, K lower Pk, same coefficient. If Kp prime is a normal compact open subgroup, and moreover, this Ecke algebra H, the abstract Ecke algebra, acts by continuous operator over the completed cohomology as well. W naught. And so what happens is that, we can define now the Ecke algebra. So we can define the Ecke algebra with infinite level of P. So let me write K upper P, W naught. This is defined as the faithful quotient acting over here. So this is the faithful quotient acting on the H tilde 1 Kp W naught, and this is also equal to the inverse limit over Kp prime of this Ecke algebra. K upper P, K lower P. So yeah, so remember that, so I can put it here. Remember that we have an injective map with dense image, Kp. This injects with dense image in H tilde 1. Remember that for the case of Shimura curve, H tilde 1 is the same as H hat 1. So here we have H upper P. So this is dense, so we have this equality. And what I would like to say is that this Ecke algebra acting over completed cohomology is actually topologically generated by the operator PL and SL. Okay, so now another remark that I would like to do is that remember, so remark, remember that at infinite level, the HI K upper P W naught is actually isomorphic to the H tilde I K upper P O tensor over O W naught. And so from now on, we can forget about the coefficients. So we have T K upper P, W naught can be just taken to be, this is isomorphic to the K, T K upper P O. Okay, so now we want to understand what happens with respect to localization at maximal ideas. So if I pick, so if I pick a maximal ideal in the Ecke algebra T K upper P O, this is maximal, I can define the localization, so H1 tilde, K upper P, W naught localized at M. So now, since here we have a projection over T, K upper P, K lower P, O, so we pull this down. So this is actually equal to the double limit. So this, what I'm doing here is I take the usual cohomology, K upper P, K lower P, W naught by S, I localize at the level, and then I take the limits. Lim here over Kp, and here I take the lim over S. So I see that there is a comment in the chat. No, okay, no. So the question is, Ecke operator only defined for degree 1 cohomology? No, you can define over all degrees. No, of course, so you're right. They can be defined over all degrees of cohomology. I'm just now. I'm stuck on the H1 because it's the only thing which are in which we are interested in. But absolutely, you are absolutely right. All right, so we have this localization. And what is important to remark is the following lemma, is that this Ecke algebra at infinite level is pi torsion free. Well, this is just because the H1 is pi torsion free. It's a unit ball in a Banach space. It is reduced and is semi-local. So the lemma is the following, is that the Ecke algebra T upper K upper P O is pi torsion free. It is reduced and it is semi-local. So in particular, the H1 tilde has a finite support. The maximal ideal in the support of H1 is finite, and hence we can break up the H tilde 1 K upper P W naught. This can be chopped up into a finite direct sum. So M, this is a maximal ideal. Maximal ideal of localization. So H tilde 1 K upper P W naught M, and this is a finite sum. Okay, so what is the key point in the proof? So keys in the proof. Well, first of all, that all maximal ideal of this EK algebra are ideal which contain P. And so I can just reduce the statement at integral at finite level. So it's enough to show that that the H1 of K upper P F has a finite support over the mod P EK algebra. Has finite support over T K upper P O mod pi. And this is once again because every maximal ideal here has to contain P. And then the second point, the second fundamental point, is that we have a smooth action over here. So the second fundamental point is that if I localize, so H1 K upper P F localize has a smooth action of G QP is smooth. And so what happens is that, well, so it's enough to show that if I take the invariant under a P group, then this is 0. So it's enough to show that there is a finite number of maximal ideals such that the following is true. So it's enough to show that there exists a finite number of M such that the H1 K upper P F localized at M, and then I take the invariant under, for instance, the principal congruence subgroup, such that this is different from 0. So now notice that I'm not taking care about the order in which I'm taking the invariant and the localization. And why? Because the localization is exact. So if I look at this space, remember that this space is actually a finite dimensional vector space. And so the annihilator of this finite dimensional vector space, well, has finite index in the EK algebra. And so we are done. But so let me write here. Whoops. So this is finite dimensional. This is finite dimensional. Because this representation is admissible. We saw that at the beginning. And so in particular, the annihilator of this H1, the annihilator of this H1 has finite index. All right, so we have this very nice decomposition of the cohomology in terms of direct sum. So now let's see the relation with Galois representation that I was mentioning just before. your pardon. So now 5.2. Relation with Galois. So now we fix once and for all a Galois absolutely reducible continuous Galois representation. So we fix once and for all a continuous Galois representation. So from Gal Q bar F over GL2 F, which we assume that it is continuous, absolutely reducible. We will see in a second that such a Galois representation will give us a maximal ideal in the Ecke algebra at infinite level, maximal ideal. And so our goal is to endow the H tilde 1 with an action, with the action of a local Galois deformation ring. So goal so we localize, so now we can localize this H1 tilde K upper PO. We localize at this ideal. We want to endow this, so this has the action, of course, of the Ecke algebra that I mentioned before, K upper PO. But we would like to construct over here the action, a map from a appropriate local Galois deformation ring. We want to construct this map. And we want to show that, sorry. So we want to show that if I pick a point in this local Galois deformation ring, so I want to show that if X is a morphism, so from now onwards, this representation, so this local representation is going to be written as rho bar. So rho bar is going to be a local two-dimensional mod P Galois representation. So if I pick a morphism from this deformation ring to O, which is a local algebra homomorphism, is a local algebra or algebra homomorphism. Here I consider O prime, so this is a finite extension. This is the ring of integer of a finite extension of E. So if I'm given such a non-zero morphism, then we have that the H tilde 1 K upper PO localized at M and the tensor R rho bar X O prime. This has O prime rank bigger or equal to 1. Has O prime rank bigger or equal to 1. So this is work of Breuil, Herzig, Yongchuan Wu, myself, and Benjamin. And Hu and Wang. Under appropriate condition on this rho bar. And in order to get there, we need to construct the following object, which is the so-called patch module. So the way to get here is to construct. So we want to construct a certain module, which is called in the literature M infinity, over what? Over our local deformation ring, so R rho bar box, and then I have to add some touching variables, so variables which come from global construction. So this object is usually called R infinity. So this is a module with the following properties. So first of all, it has a continuous action of GQP. So continuous GQP action. And moreover, what we have is the following. We have a morphism from a formally smooth ring over O, it's called S infinity. Here we have, so this is a formally smooth over O. So here we have a certain number of variables, Y, which usually are called Yi, Zi, certain number of variables. So if I consider here the maximal ideal, the augmentation ideal, this gives me a certain ideal, which is called A infinity in here. So what are the properties? I was mentioning the properties that we have a map of R infinity to the Ecke algebra, K upper P O. And the property of this object are the following. So such that, first of all, M infinity is projective. As S infinity double bracket GZP module. So this is double bracket. Huh? And second of all, if I kill the action of A infinity, I get back the completed cohomology. So if I consider this HM infinity mod A infinity, and here I take an appropriate dual, this is called the Shikov dual. The appearance of this Shikov dual is because we are working at integral level, so we need a more refined version of a duality. So this is the H tilde 1 K upper P O localized at M R bar. And this is compatible with this map. It's compatible. With this map. I have to mention that if I kill off A infinity here, I get back a surjection over the Ecke algebra localized. Sorry, this is localized. Okay, so these are the guidelines of the next 30 minutes. I would like just to mention that this object, the patch module, is something that appeared already in the talk of, it will appear in the talk of Dan, it appeared already in the talk of Christophe Proya, and in the talks of Yong-Tran and Havan. All right, so first of all, I have to mention that all the spaces, the cohomology spaces that I introduced so far, have a natural Galois action. Why? Because we're working with smooth curves. So the following is that we have the comparison theorem between Betty and the entire cohomology. So we have our HI et al. Of what? of our, remember that we have this canonical model. Here I have I extend the scalars to C. Here I consider the data shift. So this is isomorphic to this comparison theorem by smoothness to the previous space, the space we worked so far. And this is seen as a complex analytic, complex algebraic variety. So this is as yk over f is smooth. So on this space we have a natural Galois action because we can extend the scalars to f bar. And so this implies that the h tilde I k upper pw or w naught and so on and so forth. So let me write w naught by s. They have a Galois qp bar f action. So I should put a little warning here. And the warning is the following, is that I should replace, so we should replace yk c by ykc mod the connected component of the center at infinity. And we want to take a coefficient such that the kernel of the map from the center to the maximal split torus quotient is trivial. So, and the kernel of z gr to r star, so this should act trivially on W. So this is just to mention that now we should be a little careful to take coefficients so that the action of this part of the center is trivial over here. All right, so what is the upshot? The upshot is that, as you can imagine, all the constructions that we did so far are equivariant with respect to the Galois action. So the properties are the following. So first of all, the action, so the GF action is continuous. It commutes with the previous action that we had, so the reductive group action and the Ecke action. Third point that I would like just to mention is that the isomorphism that we got before, H1 KP W isomorphic to the smooth vectors of the H1 K upper P W smooth, is GF equivariant. So this is an important remark that I would like to mention here. The fact that this isomorphism is GF equivariant is a little bit delicate now. Why? Because we obtain this isomorphism via a spectral sequence, like an edge map of a spectral sequence. Well, the problem now is that this spectral sequence, so here I have to put a warning. Here we have a warning. This was obtained via a spectral sequence that I just want to recall. Stable KP H J K upper PW goes to hi plus j k upper p w. This spectral sequence was obtained by simplicial cohomology, and so we don't have a priori comparison. So the key point is that we had to give an alternative proof of this fact using algebraic method. So we need so this was given by simplicial cohomology. And so now we need an alternative proof in order to get this algebraically. So we need an alternative proof which use the Serre and then which considers a passes through the limit and then take the limit. The limit over all level at P, and then you take the limit over S. Let me say that even if this sounds easy, it's not so easy at least. In the sense that one has to be really careful, has to work in some localized categories where kernel and co-kernel are not zero, but they become zero after localization, where the morphisms are eventually zero, the transition morphisms of inverse limits. Once again, all this is proved in the reference of Hamilton. Okay. So now, what does it mean, first of all? So how can we associate an equideal to a Galois representation? So if I'm given, so I consider the following definition. If I am given a Galois representation, a continuous Galois representation, GF to GL to E, so this is modular, if it appears as a constituent in the completed cohomology, in the classical cohomology. If the Hom GF equivariant of R H1 et al K upper P W is different from zero. This implies that R is ramified almost everywhere. But now, if I consider the mod P, so what is the notion of modularity mod P? Let's write R bar is going to be the mod P reduction of a stable lattice of R. And from now on, we assume that the mod P reduction is absolutely reducible. So let's write everything. Here we have GL2F. So we assume, so this is the mod P reduction of a GF stable lattice in R, and we assume that it is absolutely irreducible. Well, then we can associate the maximal idea in the Ecke algebra, which I called M R bar. This is the kernel. It's the kernel of the following map. So from the Ecke algebra, TK upper P O to F, which associates, so TL goes to the trace of the characteristic polynomial of, sorry, this goes to the trace of R bar specialized at the Frobenius minus 1 L, and S L goes to the determinant of R Frobenius here. So here we have also to multiply by the norm of the prime L. So we have this maximality in the Ecke algebra, and we say that R bar is modular if of a certain level, if this H1 et al. K upper P F localized at M R bar is different from 0. All right, then we can, of course, try to define modularity with respect to a level and with respect to a Serre weight. And the very important thing is that if a certain Serre weight appears in the mode reduction of a Weil module, well, it's not at all clear, in general it's false, that R is modular for all the Jordan order constituent of this Weil module. So this is the problem of the shadow weights. This problem appears as soon as we leave the world of GR2. So what is important, and I would like to mention, is the following, are the following properties of the localization at the maximal Galois ideas of the cohomology. So we have some remarkable properties, which are the following. Is that, first of all, we have a natural isomorphism. So when I reduce the coefficient, mod P, well, we have a natural isomorphism between the H1 tilde. Here, from now on, well, it's the algebraic H1. So here we have H1 K upper P, W naught, localized at MR bar. So if I quotient out by pi, this is isomorphic to the H tilde 1 Kp W naught mod pi localized. And the second crucial property that I would like to mention is that the H tilde 1 of K upper P W localized is in fact isomorphic to the space of continuous function so this is as representation of H, so H is a compact open in GQP. This should be interpreted as a morphism as H representation. And here we have a direct sum for some maybe M. Sorry, maybe N for some N. So we have this isomorphism. And this actually follows from the fact that the H1 K upper P W naught mod S localized is a smooth representation which is injective. So it's a smooth, so it's a representation, smooth H representation with O mod by S coefficient, which is injective. So I just want to say a word about the proof of this, because it's an argument which appears many times. So the key point is the following. So the main idea, is that once we localize at this ideal, which is associated to an absolutely reducible Galois representation, we kill off the h tilde 0 and h tilde 1, h tilde 2. And so we get some exactness properties of the functor of completed cohomology. The main idea, so let me just write the point, is that we have an exact sequence, say W, here we have W naught mod pi S prime, so we pick S prime bigger equal than S. So here I multiply by S. Here I have the W naught mod by S. Here I have the W naught mod. So this is S prime by S. Okay. So now the point is that I pass to the longer exact sequence in cohomology, and I localize. So I get, here I have the H0 of K upper P, K lower P, V naught mod pi S prime, sorry, pi S, sorry. Here I have my H1 of, you can imagine what, H1, and here we have the H2. You can imagine what. So what is the key point? The key point is that this, remember that this is isomorphic to a direct sum of the continuous function. Sorry, it's a direct sum of function, of Kp mod H. And here we have the coefficient W naught by S. Sorry. Here we have the O Fp cross mod a certain power. And in particular, here the action is abelian, so we have an abelian action. Of GF. And so when we localize, so this implies that
maybe the bottom part is not visible. Yeah, thank you.
Thank you very much. Thank you. So what I want to say is that you remember that in the previous lecture, we saw that this H naught is actually isomorphic to a direct sum of copies of functions over the units of, so here we have some power, which depends on the level here. So remember that we saw that the H naught is isomorphic as a direct sum of this form. And so in particular, the action is abelian over here. And so this implies that the H naught localized at MR is 0. And so by Poincaré duality, also the H2 is 0 after localization. And so this implies by Poincaré that also the H2 is 0 after localization. I just want to remind you that here our curves are compact. So Poincaré duality gives us the duality with the compact H2, but here there is no difference. between compact and non-compact cohomology, because they're the same. Okay, so this is the main idea. And this idea appears also in the proof that this object is injective. All right. So now, we want to understand the relation. Yes, of course, yes. So the question is, do we assume that the maximal idea is non-Eisenstein? Yes, yes, of course, yes. So I was saying that from now on, rho bar, the Galois representation of P, is supposed to be, sure. So it's supposed to be absolutely reducible. Of course, otherwise this doesn't work. All right, so now let's go to the Galois representation. So now, for technical reason, we have to assume the following. For technical, we have to assume that R bar restricted to the Galois group Q bar, here I take F and I add the primitive P root of unity, is still absolutely irreducible. And then, for simplicity, we assume the following. We assume that our Galois representation R bar restricted at GFL is ramified for all L different from P. And moreover, we have to make the following assumption. So we have to assume that K upper PL is a maximal order. If L is different from P. So now, again, for technical reasons, we have to fix a place. So we fix a place V, I call it V1, such that the norm of V1 is not congruent to 1 mod P, and we assume that R bar restricted at G at V has distinct Frobenius eigenvalues, so has distinct Frobenius eigenvalues. So this is another technical reason which is needed in the patching constructions. So this is needed for the existence of the so-called Taylor-Wise prime. This is needed in order to get a bigness, what is called business. And sorry. This is needed in order to get a formal smoothness of a certain local deformation ring. Okay. So, so we assume that this is a maximal order if L different from P and V1, and it is a pro V Ibahori and is pro V1 Ibahori at V1. I also want to say that V1 is a place where our quaternion algebra is split. All right. So, sorry for this technical digression. So what is the point? The point is that we want to introduce some global deformation problem. So global. So we consider the deformation problem which associate to R, which is a complete local Noetherian O algebra, associate the lifts GF to G2 R. So these are lifts which are ramified outside P and outside V1. So this is the maximal ramified extension outside P and V1 with cyclotomic determinant. So such that the determinant of R is chi-cyclotomic. So what happens is that this functor is representable. This is representable by well, a complete local Noetherian algebra, which I call the R universal. I just give it a name by a complete local Noetherian O algebra. So we want now to write to have a morphism from here to our Ecke algebra, localized at M. So how do we do that? So you remember that. By the comparison theorem, we have that the H1 of K upper P, K lower P, with coefficient in W. This is isomorphic to a certain direct sum. So this is the local global compatibility. So this is a direct sum over what? Over automorphic representation, which are not one-dimensional. So this is an automorphic representation. G ad L of dimension strictly bigger than one, with the condition that at infinity, this is isomorphic to the complexification of W. And here we have R pi times R finite, and here I take K upper P, K lower P. And this satisfies the local global compatibility. So this is such that if I take the Debargha representation associated to the restriction of R pi restricted to G FL, this is equal to the local Lagrange correspondence at L with E with coefficient over the algebraic closure of the coefficient field E of what? Of pi L times that absolute value minus 1/2. So this is Caraiola. His Annales de l'ENS paper of Annales ENS paper of 86 and Saito. This is Hilbert modular forms, Hilbert modular form, and p-adic Hoche theory. So Caraiola is for places outside P, and Saito for places at P. So because of this, we can construct. So we can construct a deformation Rm GF, which takes values. So how do we construct this representation? It takes value in the product of J2E with P are as above plus some further conditions on the Satake parameter of pi L. And this is exactly the GL2 of the Ecke algebra K upper P tensor over E. And so now a technique by Carayola let us factor this map through the GL2 of T. And this is by Carayola. This is due to the fact that the trace of the Frobeni belong to this space, and so it's possible to conjugate Rm so that it takes values here. So now, given this, so let me, I can still write here. And so by local global compatibility, this deformation Rm is a deformation, is ramified outside. So it's ramified outside V1 and is a lift by construction, because we have the condition on the Satake, is a lift of R bar. And so we get the desired map. So we get the consequence by universality, we get the desired map from R not universal to the Ecke algebra. So this was, the previous was for any fixed level at P, and so we pass to the limit and we have this map, which is actually surjective. All right. So now, how do we get the flatness that I mentioned before? The flatness is obtained as follows. So now we have this morphism, and recall that we can actually, so we have a natural map from here to here given by the restriction. Here we have rho bar with some extra variables. I just want to recall you that now we have to take into account the module M infinity that I introduced just before. So here we have some extra variables. Because the flatness that I mentioned before it's obtained via the patch module. So I'm almost done. I see that I'm a few minutes late, so I'm almost done. So flatness. We know that M infinity is projective of finite type over S infinity double bracket. Here I can take a compact open subgroup, and so I take a pro P compact open, the principal congruent subgroup, mod the center. I call it ZP1. So it is projective finite type over this ring, which is local. And so this implies that this module is free over here. But since this module is free over here, it is in particular Cohomology over here. And so it's possible to prove that M infinity, so recall that S infinity acts over here through R infinity. And so since M infinity is Cohomology over here, it's also Cohomology over the ring downstairs. So M infinity is Cohomology over R infinity double bracket KP1 over ZP1. And now we have the following. So by the properties, so the properties of M infinity, we know that M infinity mod the maximal ideal and idealized, this is equal to H1 K upper P comma F, localize, Ecke eigenspace. So this is our representation. And we know, so this is, we know that the grade, the J over F, which was introduced in the lecture of Benjamin, this, the grade of this is equal to 2 FP over QP. So this is this was discussed in the talk of Yongchuan and Hauran. All right, and also what is kind of formal is that the J infinity, sorry, the J R infinity, double bracket, KP1, ZP1 of M infinity, because of this freeness result, we know that this is equal to the dimension of R infinity minus the dimension of S infinity, which is equal to FP over QP. By why do we know this? Because of the properties from p-adic, integral p-adic theory, we know the dimension of the Galois, local Galois deformation ring. And so these two quantities are equal. And so by the non-commutative miracle flatness, let me write as follows. I take the green, which I never used so far, so I end up with the green color. So these and these are equal. And so by the non-commutative miracle flatness, we know that M infinity is flat over R infinity. And this implies the fact that the rank over O, when we base change over a Galois representation, has rank bigger or equal than 1. All right, I finish here. So thank you very much. Thank you very much for having followed this course. And please don't hesitate if you have any questions.
So on behalf, before Shalini taking over, on behalf of the organizing committee, I'd like to thank Professor Morra for this wonderful course. Everything moved very fast, and it was, I think, 1 month back, I asked him to give the course. And thank you very much for this course. It was really wonderful. Thank you.
Thank you. Thank you all. Thank you all. It was a big pleasure. Thank you so much. Thank you.
We'll take over from you.
Thank you.
Yeah.
If you have questions, please don't hesitate. I can also reply by mail afterwards because I see that we are a little bit late.
Yeah, thank you, Professor Morra, for the wonderful series. And questions, please, whoever have questions.
Yeah. I had a question, Professor Morra. So this is Avik. Yeah. So this Heck algebra at infinite level, is it also complete O algebra?
Yeah. So it's p-adically complete.
Okay, so then we can also break it down as products of localizations.
Yes.
And all that. So then we can get that decomposition of the cohomology in terms of localizations through idempotents and all those things. The standard technique. Okay.
Yes, of course, yes. That's exactly why you get this decomposition of the cohomology, because you can prove that it's semi-local. So this algebra is semi-local.
Okay, and I had one more question. Did we at some point assume that the maximal ideal associated to rho bar,
yes.
I mean, when we localize H1 tilde with respect to that, it's non-empty? I mean, it's non-zero, sorry?
Yeah. Thank you very much.
Okay.
Thank you. We are assuming throughout, in all the discussion, we are assuming that R bar is modular.
Okay. So there is one modular lift. We are assuming at least one modular.
Thank you very much.
Okay.
So we assume for the whole discussion from this point onwards that R bar is modular, so this is non-zero.
Okay. Thank you. I'll email you with few more questions if that is okay.
Thank you.
Yeah, thank you. Any more questions or comments? If not, let's thank the speaker again, and we'll meet in about 1 hour. Yeah.
Thank you. Thank you. Thank you.
Okay, we'll start again at 2 o'clock Indian time in 50 minutes after the lunch break. Yeah, with Fred Diamond stuff. Okay, thank you.
Thank you. See you. Thank you.
Thank you.